Hello, science fans. Today, we're diving into the electrifying world of electronics. Think about the power that comes out of the wall socket in your home. That's called alternating current, or AC for short. It's like a tide that constantly flows back and forth, changing its direction many times every second. This back and forth flow is great for sending electricity over long distances, but most of our favorite gadgets, like our phones, laptops, and video game consoles, can't use it directly. They need a different kind of power, one that flows in a single, steady direction. That's where the hero of our story comes in. This steady, one-way power is called direct current, or DC. Imagine a river that always flows downstream. That's DC. It's the kind of power that batteries provide. So, how do we turn that back-and-forth AC from the wall into the one-way DC our electronics crave? We use a process called rectification. It's a fundamental concept in electronics, a bit like being a traffic cop for electricity. The job of a rectifier is to take the two-way street of AC and turn it into a one-way street of DC. It's an essential transformation that happens inside almost every electronic device you plug into the wall. The main component that makes this magic happen is a tiny electronic gatekeeper called a diode. You can think of a diode as a one-way door for electricity. It allows the current to flow through in one direction, but slams the door shut if the current tries to flow back the other way. This simple but brilliant property is the key to converting AC to DC. By strategically placing these diodes in a circuit, we can control the flow of electricity and force it to travel in only one direction. This is the very heart of rectification, a process that powers our digital lives every single day. So, to recap, our wall outlets provide AC, which alternates its direction. Our gadgets need DC, which flows in a single, constant direction. Rectification is the process of converting AC to DC, and the diode is the special component that makes it all possible. It's a remarkable bit of science that takes place silently inside the power adapters and chargers we use constantly. Without this crucial step, the modern world of electronics simply wouldn't work. Now let's take a closer look at the simplest way to do this: half-wave rectification. Consider it. Let's start with the most basic form of rectification, the half-wave rectifier. As its name suggests, it only uses half of the incoming AC wave. Imagine you're playing catch with a friend, but you only catch the ball when it's thrown to your right hand. Every time it's thrown to your left, you just let it go by. That's essentially what a half-wave rectifier does. It uses a single diode to act as that one-way gate. When the AC current flows in the forward direction that the diode allows, the electricity passes through. It's like the door is open, and the current can go on its merry way. But remember, AC power is constantly switching directions. So, what happens when the current tries to flow in the reverse direction? The diode slams the door shut. It blocks the flow completely. This means that for half of the time, no electricity gets through the circuit at all. The output is a series of positive pulses, with big gaps in between where the negative half of the AC wave used to be. It's like getting a series of pushes, but with long pauses in between each push. You get some power, but you're missing out on a whole lot of potential energy. This method is very simple to build. It only requires one diode, making it inexpensive and easy to implement in basic circuits. However, its simplicity comes at a cost: inefficiency. Because it throws away half of the AC power cycle, it's not very good at delivering a smooth or powerful stream of DC energy. The resulting DC output is very lumpy or pulsating, which isn't suitable for most sensitive electronic devices. Imagine trying to run a toy car that only gets power half the time. It would move in a very jerky, start and stop motion. Because of this inefficiency and the pulsating nature of the output, half-wave rectifiers aren't used for powering complex devices like computers or smartphones. However, they do have their place in some very simple, low-power applications where a rough DC signal is acceptable. For example, they might be used in simple battery chargers or basic power supplies for projects that don't require a steady flow of energy. It's a good starting point, but for most of our modern needs, we need a way to capture all the energy the AC wave has to offer. So, if half-wave rectification is like catching a ball with only one hand, how can we do better? By using both hands, of course. This is the idea behind full-wave rectification. This clever method is designed to capture and use both halves of the AC wave, making it much more efficient. Instead of blocking the negative half of the wave, a full-wave rectifier cleverly flips it over. turning it into another positive pulse. This means you get a continuous stream of DC pulses without the long gaps we saw in the half-wave output. It's a much more effective way to harness the available power. There are two main ways to build a full-wave rectifier. One way uses a special component called a center-tapped transformer and two diodes. The other, more common method is called a bridge rectifier, and it uses a smart arrangement of 4 diodes. Think of this bridge of diodes as a clever system of one-way streets. No matter which way the AC traffic is flowing, forward or backward, the bridge directs it so it always comes out on the same one-way road. It takes the alternating flow and ensures the output is always pushing in the same positive direction. The result is a DC output that is far smoother and more powerful than what a half-wave rectifier can produce. While the output is still a series of pulses, these pulses are now twice as frequent, filling in the gaps that the half-wave rectifier left behind. This makes it much easier to smooth out the final DC signal. We can add another component, a capacitor, which acts like a small temporary water tank. It stores energy during the peaks of the pulses and releases it during the valleys, smoothing out the flow into a much steadier stream of DC power that our electronics can happily use. The benefits of full-wave rectification are huge. The efficiency is doubled because we are no longer wasting half of the power. The output is more consistent and easier to smooth, leading to a higher quality power supply. This makes full-wave rectification the standard for almost all consumer electronics. The power adapter for your laptop, the charger for your phone, the power supply inside your television, they all rely on full-wave bridge rectifiers to do their job reliably. It's a brilliant piece of engineering that powers our modern world. Now that we understand the science, let's look at where these rectifiers show up in our daily lives. As we mentioned, half-wave rectifiers, with their simple but inefficient design, are found in places where power requirements are minimal and cost is a major factor. Think of simple applications like a basic soldering iron that just needs to get hot, or perhaps a simple LED indicator light circuit. They are also sometimes used in signal detection circuits, like in an old AM radio, where their job is to extract the audio signal from a radio wave, a process called demodulation. Full-wave rectifiers, on the other hand, are everywhere. They are the unsung heroes inside virtually every device that plugs into a wall outlet but runs on DC. Take a look at that little black box on your laptop's power cord. That's a power adapter. And inside it, a full-wave bridge rectifier is hard at work, converting the 120-volt or 240-volt AC from your wall into the low-voltage DC your laptop needs to charge its battery and run its components. The same goes for your smartphone charger, your video game console's power brick, and the internal power supply of your desktop computer. But their applications go far beyond personal electronics. In the industrial world, full-wave rectifiers are used to power DC motors, which are used in everything from elevators to electric vehicles. They are also essential in welding machines, which require high current DC to create a stable arc. Even large-scale power systems use rectification. For instance, in high-voltage direct current, or HVDC, power transmission, massive rectifier stations convert AC to DC to send power efficiently over very long distances, and then another station converts it back to AC for local use. In conclusion, rectification is a fundamental process that bridges the gap between the AC power grid and our DC-powered world. While the simple half-wave rectifier has its niche uses, it's the efficient and robust full-wave rectifier that truly makes modern technology possible. From the tiniest phone charger to massive industrial systems, these clever circuits are silently and reliably converting power, ensuring our gadgets and machines get the steady, one-way flow of energy they need to operate. It's a powerful reminder that sometimes the most important science is the science you can't even see. Science rules.